Okay, so let's just go over some of this real fast. Okay, so if you have the projection map from Z to Z3, okay, clearly the image is Z3, the kernel is all multiples of 3. So the isomorphism that you get from the ring isomorphism, the first theorem of ring isomorphisms is the domain modded out by the kernel is equal to the image. Okay, everyone okay with that? Here, if you have the zero, this is called the zero map. Okay, it's also called the trivial map. Okay, so if you send everything to 0, then 0 is the image. The kernel is everything, and so you have this interesting equation. This is basically saying that r divided by r is equal to 1, where 1 is the number of elements in here. Okay, so it looks a little funny, but that's correct. Okay, now in this case here, there's one tiny thing. Okay, the phi goes from r to r. Okay, that's the identity map. Okay, phi of r to r. The image is all of r. The kernel is trivial, so therefore you get this equation, which is essentially saying r divided by 1 is r. Okay, so for isomorphisms, let's put 2 arrows here. I mean 2 lines. Hi, CC. How are you? All right. So here, if I have a homomorphism from R to S, okay, the kernel is the set of all things in the domain that gets sent to 0. Okay. So so we have we want to show that it's non-empty. Okay. So the way that you show that 0 is in K is that you apply. Oh. Oh, I see, I see, I see. Typically, what you do is you do this, right? You see that? Yeah. So you basically say, okay, I'm going to add, wait, how does this work? Phi of 0, I see. You're using phi of 0 is phi of 0 plus 0, which is equal to phi of 0 plus phi of 0. And then you cancel a phi of 0 from both sides, right? And then you get this. Good? Okay. And then here, you take 2 elements, right? And did you quantify R? Right? Oh, yeah, you need to quantify R. Okay? So you need to show that phi of the sum is equal to 0 as well. It's a little bit better, right, to put a minus sign here, because if you're using the 1.5 subgroup test, that's what you need. And then here, okay, you're pulling this out. Good. Okay. Everybody understand this? Okay. So let's talk a little bit about these. So number 4 on your homework, right? Number 4 on the homework is something that you have to LaTeX up, okay, on your own. Talks about this thing called, okay, the set, okay, U of R, okay, if R is a ring. Now again, we're assuming that R is commutative and unital. Okay, so here, okay, U of R is a set of all R and R, okay, just that R has a multiplicative inverse. Okay. Okay. So everybody okay with that? Okay. So in the case when R is a field, okay. Okay, what is U of R? Huh? R minus 0. Okay, so that's given by R star. Okay, does it make sense? Right? So in a field, everything has a multiplicative inverse except for 0. Right? So so this called, okay, this U of R, okay, is called, okay, the group of units. Okay. Now we have not shown that it is a group yet, okay, but that's the content of number 4 on the homework. You have to show that it's an abelian group. Okay. Okay. So okay, but in certain cases, right, you have to actually compute. So for example, okay, if R is equal to Zn, okay, and here n may not be prime, okay, then. Right? Then what does this mean? Okay, then U of R, okay, is equal to the set of all elements in Zn. Now, what numbers in Zn have multiplicative inverses? 1. All right, can you characterize them in some way? Yeah?
The numbers that are relatively prime.
Right, so R, okay, that are relatively prime, okay, to n. Good. And how many of them are there? Phi of n, okay, so there are, and, okay, the number of elements in U of R, okay, is equal to phi of n, okay, where phi is the, what is that called? The Euler-Toshin function, okay. Okay. It's the only place in the English language where the word totient is used, okay, although the word quotient is used all the time. Yeah.
But is it not the only place in Latin where totient?
No, totient, well, yeah, so in Latin you have quotients and you have totiens. Okay, so yeah, that happens all the time. Okay. We could talk about those kinds of words later, okay. What else can I say? Nothing. Okay, so recall, okay, that, okay, if P is prime, okay, then phi to the P to the n, okay, I don't know, remember if everybody remembers the formula, okay, it's P to the n minus P to the n minus 1, okay? So another way that you can write this is P to the n minus, like this. Okay, just factor out a P to the n, okay? And, okay, phi of P to the n, Q to the m, okay, is phi to the P to the n called times phi to the Q to the m, okay, if P and Q are relatively prime. Relatively prime primes. Oh, well, you know what I mean, right? R, how about R distinct primes? If P and Q are primes, how do I say this? If P and Q are primes with P not equal to Q. Or distinct primes, how about that? Okay. Oh, geez, okay. Oh, this is being recorded, okay. Everybody okay with that? All right, so what is it called when a function breaks up like this? It's called multiplicative. Okay, it's called multiplicative. Okay. All right. So for example, okay, here's an example. Okay. So determine, okay, what group, okay, is U of Z, I don't know, Z, let me think of a non-terrible number, 9, okay? I don't know if that's on your homework, okay? So what do I mean by this, all right? So let's figure out what I mean by this, okay? So first of all, right, I want to figure out how many elements there are, okay? So we know that, okay, phi of 9, okay, is equal to 9 minus what? 1, 2, 3, okay? No, the way you do it is this, right? It's 3 squared is 3 squared minus 3 to the first power. So it's 3, right? Okay, so this is 6. Oh, that's not such a fun example, okay? Because then, okay, well, what are the, so since, okay, U of Z9, okay, is abelian, okay, it must be isomorphic to an abelian group of order 6, okay? Now, what are the abelian groups of order 6? So Z3 cross Z2, or Z6. Anybody going to complain about anything? No? Complain? Okay, these are the same. Okay, these are the same. Why are they the same? They're both cyclic, right? Okay, this is generated by 1, 1, and this is generated by 1. Okay, right? If you have cyclic groups, right, of the same order, they're isomorphic to each other just by sending the generator to the generator. Make sense? Okay, so this guy has to be isomorphic to Z6. Make sense? Okay. All right. So, how about u, I'm trying to find, what is phi of that? 15 times 4/5 times 2/3 is 8. No, that's no good. I need something non-stupid. Is that in the homework? Oh, well, if it's on the homework, it's on the homework. Okay. Well, Z12. What is phi of 12? Isn't it? What is phi of 12? Okay. Phi of 12 equals phi of 3 times phi of 4, which is 2 times 2. All right, that's fine, which is a 4. Okay. So what are the possibilities? Okay. Are what? U12 is isomorphic to, what's one possibility? Z cross Z2, or, Lauren? Z4, okay? Now, notice that this guy is not cyclic and this guy is cyclic, okay? These two are very different. So how do you figure out which one it is, okay? So what you want to do is you want to take a look at the 4 elements of Z12, okay, that are, of UC12. So U of Z12, okay, consists of 1. What else is coprime to the 12? 5, good. What else? 7, 11, okay? So note, okay, that 1 squared is 1, 5 squared is 25, which is 25 in Z12, 1, okay, right? And I know that 7 squared is 1, okay, and 11 squared is 1, okay? So what does this tell you about this group, okay? Every element has, is an idempotent. No, an idempotent means E squared equals E. Everything is its own inverse, okay? And what happens, which one is that? That's Z2 cross Z2, okay? So U Z12 is Z2 cross Z2, okay? So you're going to have to use the theory, the fundamental theorem of abelian groups to do this problem. Is that clear? Okay. All right. So okay, so we have a notion. Let's talk about polynomials for a bit, okay? Okay, so for polynomials, okay, so let R be a ring, okay? Okay, and let Rx be its polynomial ring. Okay, so we know that we can give R of x an addition. We know how to add polynomials, okay? And we define a certain multiplication, okay, that makes this into a unital ring, okay? It's also a commutative unital ring. Okay, make sense? All right, so what I want you to do, okay, so an object, okay, in R of x is called something like P, okay? Something called P. Now, what does P look like? P looks like something of this form. Right? Phyllis is okay? Now, notice that I wrote P instead of what? P of x. Okay? Notice that there are x's here. I did not write P of x, not P of. Why did I do that? No? Okay? Yeah. Yeah, P of x is a function, sort of, right? And I am not thinking of these as functions. Okay? I'm thinking of them as objects. Okay? And objects, I don't care what the x's are. Okay? But I just consider this to be one object, and it's called P, and that's it. Okay. However, right, occasionally you will want to plug in a number for x, right? And that is, when we do that, we're basically treating this object like a function, okay, like a function. But I don't want to reduce this just to a function object. I'm trying to say something very subtle here. This is what I'm trying to say. Okay. All right. Like let C be an R. Okay. Suppose we want to take an object in my base ring and I want to plug it in here. Okay. Then, okay, we're going to write this notation, which nobody uses except for me, but I think it's going to be clearer sometimes. Is I'm going to take P, I'm going to slash it, I'm going to put a C there, and that is what I mean by this object right here. Okay? There's nothing deep about what I'm saying. All I'm saying is notation. Okay? So in this class, we will use P slash C to mean this object, unless I mistakenly put something else in the homework, okay, and then you'll correct me. Okay? Instead of, okay, P of C, okay? Does that make sense? That's all I'm trying to say. That's all I'm doing, okay? So, right, so note, okay, that if P and Q, okay, are in Rx, okay, and C is in R, okay, then it is not hard to convince yourselves that when you take P plus Q as polynomial, abstract polynomial objects, and you put a C in there, okay, what happens? It's simply P slash C plus Q slash C, okay? Nothing deep, okay, nothing deep. Just new notation. PQ slash C is P slash C times Q slash C. Okay? Does that make sense? Where is this addition happening? What set is this happening in? It's happening in R. Okay? So basically what I'm saying is the following. Okay? The process of slashing by C, okay, is a ring homomorphism. Okay? So this implies, okay, that that what we call evaluation at C, okay, is a ring homomorphism. And what does it look like? It's called evaluation at C, okay, colon, what object do I take when I evaluate at C? I take a polynomial and I spit out an element of R. Okay? So, right, given by eval C of F is equal to F slash C. Okay? That's all I mean. Make sense? Everybody okay with that? Okay, so that's an example of an important ring homomorphism. Okay? Now, let's talk about what it means to be a root. Okay? So here's a definition. Okay. So suppose, okay, that F is an element of Rx, okay, and C is an element of R. If F slash C is equal to 0, okay, that means you plug in C and you get 0, right? Then what happens, right? C is called a root, okay, of F. Okay? So in this course, we're going to be talking a lot about roots of objects. Okay? Make sense? Okay. So let's prove this claim right here. Okay? So let R of X be a polynomial ring. Okay? Okay, and let C, okay, be an R. Make sense? Okay. So let, okay, IC, okay, be the set of all F's in Rx. Okay. What do you think I want to do with? How do you think I want to relate F with C? F slash C is 0. Okay. So I want to look at all polynomials, okay, for which C is a root. What are you saying?
I said, spoiler alert, it's an ideal.
It's an ideal. Okay, then IC, okay, is an ideal. Okay, ideal. All right, so the collection of all things, okay, that I call it kill, okay, killing, right, sa, right? So if you want to kill C, all the things that kill C, all right, forms an ideal. So let's prove this. Okay, how do you know that this guy is non-empty? Can you give me an element in it? The zero. The zero polynomial kills C. What's a non-zero thing that kills C? Can you think of a polynomial that kills C? X minus C. Okay, so proof. Okay, so clearly, right, 0 belongs to IC. Okay, as does X minus C. Okay, so IC is non-empty. Okay, right. Then, right, let's pick a few things. Like let's take F G in IC, and let's take an H in R of X. Okay, I want to prove that F minus G is in IC. So F minus G, I'm interested in knowing what that does to C. Right? Oh, what did I write down incorrectly? It's a slash. Okay, so you're already screwing up. So slash. And that's equal to F minus C minus G minus C, which is 0 minus 0. Okay. And HF slash C is H of slash C times F slash C. What's H slash C? Nikki, we don't know. Okay, so we just write it over again. But then we're multiplying by 0. Okay, so we get 0. Okay. All right, so that's it. Everyone see that? Makes sense? Everybody okay? All right. So here's a claim. Okay. So here's a definition. Okay. Let F, okay, be an R of X. Okay. I'm not going to say let R be a polynomial. Blah 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 blah. Okay. Let F and let C be an R. C be a. Did I say root? Did I define what it meant to be a root? Okay. A root of F. Okay. Then X minus C divides F. Okay. Does that make sense? Okay. X minus C divides F. Oh, wait. That's not a definition. That's a theorem. Okay. Sorry. So here's a claim. Okay. So let's talk about this for a second. Okay. So let's talk about X minus C slash F. I want to know about this guy right here. Okay. So consider the division algorithm. Okay. Applied to F and X minus C. Okay. So what can you tell me about? Sorry, F. Okay. So why was it wrong to write R? Huh? So. Yeah.
That's not.
If I just wrote R, why is this theorem false? Oh, why is this technique false? Yes.
I was going to say 0 minus 6 is that the problem?
Yeah, it is the problem, but something more general. Well, kind of. No, because no. If it were Z of X, okay, I would still be wrong.
Oh, you need to have a division algorithm.
You need to have a division algorithm, okay? The only way that you have a division algorithm is if this guy were a field. Does it make sense? Okay? If you don't have a field, you can't do division algorithm. Hello? No?
Okay, yes.
Are you? Suppose I were asking you to divide these three things, okay? Right? In Z of X. Okay? Could you do it? No, because you would have to put a 1/2 X up here and you don't have a 1/2. Okay? Right? So the division algorithm does not work, right, unless this thing over this ring is a field. Okay? Make sense? Okay. So if you're a field, okay, let blah, 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 then X blah, blah, blah. Okay, consider the division algorithm applied to this, okay? Okay, so let's talk about what that means, okay? So what does the division algorithm give us, okay? Therefore, there are polynomials q and r in fx such that, tell me what you get. You get, let's make f the bigger one. F equals q times x minus c plus r, okay, where the degree of r is less than what? The degree of what? Which is? Correct, okay? So the degree of r has to be less than 1, i.e., okay, the degree of r has to be 0. What? Basically, what do you know about r? What kind of object is r? It's a constant. It has to be a constant, okay? Its degree is either minus infinity or it's 0, in which case it's a constant, okay? R is a constant. Okay, well, let's figure out which constant it is, okay? Now, let's slash everything with c, okay? Then f slash c equals q slash c times x minus c slash c plus r slash c. Okay, now here's one of these places where it's important that we use the slash notation instead of the other one. If I wrote q of x minus c here, do you see how this might be confusing? Okay, because if I used q in a loose and fast way, this notation you might not think of as q times x minus c, but you might think of it as q of x minus c, where you take q and you plug in x minus c, right? So whenever you see this, okay, it is not that notation. It's this notation right here. Okay, so what is q slash c? We don't know, okay? What is x minus c slash c? Okay, that's 0, okay? And r slash c, we don't know, okay? All right, and then what's f slash c? 0, okay? Hence, okay, hence what do we know? R slash c is equal to 0, okay? But remember, r is a constant, okay? So when you have a constant and you stick in c, what do you get? You get the constant, okay? So that means that r itself has to be 0, okay? Why do I want r to be 0, okay? Because if you look back here, right, oops, at the division algorithm right here, so, okay, f is equal to q times x minus c, right, i.e. x minus c divides f, okay? So here's the punchline, right? So here's just the moral, okay? So the moral is that if f, okay, if c, okay, is an element of f, is a root of a function, a polynomial in here, okay, then f is equal to x minus c times q for some q in fx. Okay? You've known this all along, right? Okay? Right? Everybody okay with that? I mean, you've known this since junior high school, yeah? That if I plug in the number, right, then I can do long division and then my remainder is 0. But the reason for that is the division algorithm, right? Over fields. Okay. Make sense? All right. Okay. Let's talk about generation. Okay, generation. Okay. Let's talk about generation in the notion of groups first. Okay. So, in the group context, okay, let G be a group. Okay? Now, if I don't tell you what the operation is, okay, do you use additive notation or do you use multiplicative notation? You use multiplicative notation, okay? Right, so I don't tell you what it is, you use multiplicative addition, okay. And let G be G, okay? Now, there is this object, okay, that you studied that's denoted this way. What is that thing? We're in a it's not this ideal, it's a cyclic group, right, generated by G. What does that mean? typically what it means, right, is it means all possible powers of G, right? So it looks like this, okay? You're taking all possible positive and negative and zero, yes.
But the negative powers. Okay.
So, right, so some people write things like this. So when you raise this to the 0th power, you get E, right? So you get G squared, okay? Like that? Want to see that? Now, what's deceptive about this notation right here? What does that look like? What does the set look like? It's, huh? No, what does it look like? This set looks, I'm trying to find a word that starts with an I. Huh? Infinite, it looks infinite. But it actually might not be infinite, right? Because if G were a finite group to start with, right, then these numbers start to repeat themselves. Does that make sense? Okay, so this guy may not be infinite. So this guy is a little bit cleaner notation, although it kind of still looks infinite. Okay, does everybody understand this set right here? Should we do an example? Okay, so an example, right, is if G is equal to Z12, okay, and G is equal to, say, 5, no, let's say 4, okay, then thingy G, right, is equal to 0, 4, 8, that's it, okay? Make sense? Okay, good. All right, so this is the thing that's given by this. Now, the thing is, right, the claim here, right, that should not be that hard, okay, that this thing right here, so far we just know that this is a definition, okay? So now we define, right? Let's just say we define this, okay? This guy, right, as Lauren said, is a subgroup, right? And let's just show that it's a subgroup real fast, okay? It is a subgroup, okay, of G, okay? So clearly, okay, G belongs to here, so it's non-empty. Okay, so now let's take two elements in here. Let H and L, well, J and K be elements of G, right? What does that mean? That means that there are, say, A and B, or how about N and M, okay, such that, what do we know about J? J is equal to G to the N, right? And K is equal to G to the M. And what am I interested in looking at? I'm not interested in looking at JK. What am I looking forward to? What is the 1.5 subgroup test? JK inverse, okay, then. So for those of you who have no idea what the 1.5 subgroup test is, okay, when you want to do a subgroup test, you have to show that it's not empty. That's the 0.5, right? And here's the 1. Okay. All right, so that is equal to G to the N times K to minus M with G to the N minus M, right? And that's in here. Okay, so that's why. Okay. So there's another way of talking about this notation. Okay, another way. Okay, of discussing, okay, this notation, okay, G, right, okay, is the following. Okay, let me just say, so this is all the powers of G. Okay, what would this notation be like that? It's the smallest subgroup in both G and, so it's the subgroup generated by G comma H, G and H, right? So it's all the powers of G, it's all the powers of H, it's all the possible multiplications that you can do with G and H and the powers of those things, right? So a faster way of saying this is it is the smallest subgroup, okay, right, that contains both of these things, okay? So another way of discussing this notation is the following, okay? Forget about powers, okay, is the following, okay? Well, actually, let's not forget about powers, okay? So G, right, is the intersection, okay, of all subgroups containing okay, G and containing G. Okay. Does that make sense? So basically what we're going to do is the following. You have a group here, okay? You have a group here, you have G, okay? What this set denotes, right, is you're going to take all the subgroups that contain G, okay? Right now, the intersection of subgroups is a subgroup by the 1.5 subgroup test, okay? The intersection of these subgroups is this guy itself is a subgroup, okay? And so what we're going to do is we're going to define that object there to be the intersection of all subgroups containing G. Make sense? Okay? Yeah? Phyllis? Is that okay? All right. So let's see how a proof like that would work. Okay? So define, all right, as before, okay, G. Well, how do I do this? Okay. We claim, okay, that G defined in this way, okay, equals the set of all Gn such that n isn't. Okay. So let's be a little bit. Let's figure out what's going on here. Here I made the definition that this was equal to this, which is perfectly fine. Okay. Here I'm not defining this way. I'm defining G this way. Does that make sense? This is my new definition of G. This is a new definition. Okay? And I want to show that with this new definition, I get this as a result. Does that make sense? Okay? So let's do it. All right, so here's the proof. So what do we want to show? We want to show, okay, that this set, G to the n, okay, is equal to the intersection, now let's see how I write this, of all subgroups, okay, H alpha, where H alpha is a subgroup of G, okay? This alpha is just an index, okay? Now, what do I know? What kind of subgroups do I want to intersect? I want to intersect all possible subgroups that do what? Someone? That G, okay, that contains G, like this. This is what I want to prove now. Does everybody understand? This is a difficult point, okay? It's a little messy. Okay, that's what we want to prove, okay? All right. Okay, so let's do it by double inclusion, okay? So let H be on the right side, okay? G to the n such that n isn't, okay? So there is an m in Z such that, okay, H equals, you'll see that this is absolutely trivial, okay? Okay? Now, how do I show that H isn't here? How do I show that H is in an intersection? That H. In general, how do I show that something's in the intersection? You show that it's in all of them, right? So take something like this, okay? So let H alpha, okay? Let H alpha be a subgroup in G, okay, with G in H alpha. Does it make sense? Okay. Does H belong to so what do I want to show? I want to say something about this H. What do I know? What do I want to know about this H? That it's an H alpha. Is it? Well, G is an H alpha. So by closure, okay, by closure of the operation, H equals G to the m, okay, has to lie in here. Lauren, is that okay? Right? So what have I just proved? Therefore, H belongs to the intersection of all possible H alphas, okay, where H alpha lies in G and G lies in H alpha. Okay? That's completely difficult to look at, but trivial. Everybody okay? All right. let's go this way. Okay. Right? So let's take a look at an element here. Okay. So let H, okay, let me think about, so we proved one direction. The other direction is obvious, okay? Why? What do we know about this guy right here? This guy right here is I'm sorry? It contains G. What else do we know about it? It's a subgroup, okay? So note, okay, note that, okay, this thing right here, okay, contains G, okay, and is a subgroup of G. Everybody agree? Right? We showed that it was a subgroup earlier. Therefore, okay, this guy right here is equal to an H alpha for some, right? For some alpha. Okay? Well, this H, well, let's call it beta, okay? Beta. So H beta, what? So H beta certainly contains the intersection of all possible H alphas, right? Okay, H alpha is in G, and G is in H, sorry, it's so small. G is in H alpha, okay? Okay? So H beta is one of these guys. The intersection of all of these guys is certainly less than one of them. Okay, so that's it. Yeah? Okay, this looks unnecessarily confusing at the moment. Okay, so let's do this in the sense of ideals. Okay. Okay. So in ideals, right, instead of using these pointy brackets, we use round brackets for whatever reason. Okay? Different books will do different things, but in this course, we'll use round brackets. Okay. So let R be a ring, just any old ring. Okay? Okay? And let, say, B be an element of R. Okay? Then we define, okay, B, okay, to be the following, okay, the intersection, okay, of all ideals of R containing B. Okay, i.e., right, what are we going to say? So here it doesn't make sense to talk about just powers of B, right? That's not going to work. Okay, so I'm going to define. Here's my definition. Okay, the intersection of all ideals. Okay, there's no notation like this one right here. Okay, so I have to write the word ideal that contains B. Make sense? Okay. Now look what I did here. Okay, right here, I had a guess. Yeah, I had a guess that this was the right answer. Yeah, here I have to figure out what the guess, because if I just said, oh, you know, I'm in Z and I'm just going to give you like 5, right? Like, okay, so what is that, right? Well, what is that? Can someone tell me what the elements of this is? Anyway, Ming Jae, do you have an idea? With that, so 5, right? So what Ming Jae is saying is that it looks like all elements of this form. Does that make sense? Okay. So what my guess is it's going to be all possible products of B with something else. Okay. So here's my claim. Okay. My claim is that in the above situation, sit to a Sean, okay, B is equal to the set of all RB, okay, where R lies in R. So all R multiples of B. Is that clear? R multiples of B. Okay. All right, so what I'm interested in showing, okay, so we want okay, to show that RB, R and R, is equal to the set of all things that look like this, okay, like that. That's what we're interested in. Okay, same idea. Okay, same idea. All right. Let's just make sure that we know how to do this. Okay. So let's go this direction first. Okay. All right. So let C, okay, be an element of the left side. Okay. All right. So so what do I write next? There is, maybe I'll use a different letter, S in R, such that what? C equals SB. Good. Okay. Now I want to show that S, not S, C is an element of this intersection. So I pick one. Okay. So let I alpha, okay, be an ideal, okay, containing B. Yeah? Right? Now, what is B? Okay, B is something in an ideal. C is a product of something with B, so therefore what can you conclude? So C, by stupidity, right, C is in, so by stupidity, so C lies in I alpha. Make sense? Okay, so what did I just show? I think I'm done, right? So C, okay, lies in the intersection of all possible ideals, okay, that contains B. Okay, easy. Hard, but easy. When I first looked at this, when I was a student, I'm like, what? Everyone okay? All right? It's messy. There's no better way of writing this down. How do we do the other way? There's one thing that we should check first, and that is what? That this guy's an ideal. Yeah? Okay. So let's check. We check, okay, that RB, okay, let's give it a name. Okay, let's call it JB. Okay, RB, R and R is an ideal. Okay, right? So clearly it's non-empty, right? All multiples of B, non-empty. Okay, so clearly, okay, JB is non-empty. Okay. All right, let's take a couple elements of it. Okay, let's C1, C2, right, be elements of JB. Okay, and I want another element, say T, to be an element of R. Okay? So then, okay, what does it mean to be in JB? Okay, there are S1 and S2 in R such that C1 equals S1b and C2 equals S2b. Okay? So I'm just being very explicit about what these C's look like. What should we do with these C's now? Anyone? Subtract them, good. So C1 minus C2, okay, is, as anyone can see, S1 minus S2 times B. What do we know about S1 minus S2 times B? It's in JB, right? Because JB is just all multiples of B, okay? And also, okay, we're interested in computing what? T times, what the hell? T times C1, okay? Also, T times C1, what's T times C1? T times C1 is T, and C1 is S1b, okay? So again, I have a multiple of B. Okay, so this guy's in JB. Okay. Right, so that therefore we've checked it, okay? Hence, JB is an ideal. Okay, right? So JB, so, and therefore, okay, JB, okay, well, what do we know about JB? JB, okay, this guy right here, okay, is such an I alpha. Okay, so JB is an ideal. Does JB contain B? Does JB, does this guy contain B? Why? What's R? 1. So if you have to be unidal for all of this to work. Okay? If you don't have that, then you're screwed. Okay? So JB, okay, JB is an ideal, okay, containing B. Okay, so JB is one of these I alphas, I betas for some beta. Okay, so therefore, JB, okay, contains the intersection of all of these guys, right? Make sense? Okay, so for the homework, okay, right, what you're going to do is instead of looking at one object, you're going to be looking at n objects, okay? And so, right, you're going to define this way, and then you're going to have to figure out what this is. Here we guessed, right? So Minjae helped us guess, right, this one. You're going to have to guess what this is. Okay, it's not hard. Okay, let's talk about asking questions. Okay, so number 11 on all of your homework assignments is ask a question. You do not get credit for asking the questions correctly. But if you do not ask a question correctly, you get negative points. Okay? Yes. And if you ask a super good question, I'll give you extra credit. Okay. So this is what I mean by asking a question. Okay? I have tried to do this with students before with utter disaster. So we'll see if it's... that's because I gave no guidance. Okay? And here, let me give you some guidance. Okay. So here's an example. Okay. So you're a monk. Okay, and you're playing with numbers, okay? And you define a number to be perfect, okay? We define, okay, an integer, okay, n greater than or equal to 1, okay, to be perfect, okay? If n happens to be the sum, okay, of all of its positive divisors, okay, that are not n itself. Proper divisors. Okay, so let's see what I mean by this. Okay, so we say that a number is perfect if you take a divisor, you take all possible divisors that are bigger than or equal to 1, no negative numbers, okay, and you're not allowed to choose the top one, okay, and then you add them up and you get itself, okay. So for example, what's the smallest perfect number? 6. Okay, 6 equals 1 plus 2 plus 3, okay. So this is saying that in this case, a number is perfect if it is exactly the sum of its parts, okay? So notice that this is an interesting concept because 1, 2, and 3 have to do with the multiplicative structure of 6. And you're adding them. So you're mixing plus with times. Do you see that? What's the next one? 28, okay, 28. So 1 plus 2 plus 4 plus 7 plus 14. Is that right? What's the next one? 400 something. Okay? 496. Okay? Someone figured this out. And one more was known in Greek antiquity. That was, anyone know? 8,128. Okay? So these were known to the Greeks. Okay? So you're a Greek, someone, a monk, whatever. You're a French monk. And you see these 4 numbers. Okay? And now you start asking questions. Okay? So I have 4 numbers that are perfect. Okay? So for each of these exercises, I want 3 questions. Okay? Right? So let's practice. What are some questions you can ask if you were a monk? And they have to be yes/no questions. Is the set of infinite, okay, so are there infinitely many? Okay? So before you ask, are there infinitely many, maybe you should ask something a little bit easier. Yeah.
Oh, I was going to say, are there bounded gaps?
No, that's too hard.
Are there any more than that?
How about what's the next one? Is there a next one? I would try to find a next one, like 5 or 6 of them, before I ask whether there are infinitely many of them. Okay? Does that make sense? Okay? Okay. Okay. Is there a 5th one? Okay? And then maybe after you get 5, okay, you can ask whether there are infinitely many. What other questions can you ask? Look at these numbers. Yeah.
Are they all even?
Are they all even? Good. Okay, are they all even? Now, okay, so if you asked this question, is there a fifth one? Okay, I would check it off. Okay, if you asked this one, I would check it off. The reason I would check these off is that these ones were answered in the 1800s, but this one is not answered yet. Okay, so if you ask a question, right, that nobody knows the answer to, I'll give you an extra credit point. Okay. The answer is we don't know. Okay, now what's another question you can ask? No? Look at these numbers. Don't they resonate in some way? Huh?
Well, aren't they all ended by 6 and 8?
Do they all end with 6 and 8? Excellent. Okay.
6 and 8 alternate.
Okay, excellent. Those are two excellent questions. Do the even ones, okay, all end in 6 or 8? Okay. The answer is yes. The answer is yes. You can prove that. Not so hard. What's the fifth question? I heard you say.
Well, I was like, suppose we assume that they're all even.
Yes.
And
Do the even ones?
alternate.
Do the okay? Do the even numbers? Do the even ones? Okay. Alternate. In what?
With the last digit.
In 6 and 8. Okay. And the answer is no.
Can we define it as a sequence?
Huh?
Can we define it as a sequence?
Can we define it as a sequence? Okay. So what you're saying is there a formula?
Is that a formula?
Okay, so that is always a really tricky question to ask. Okay, is there a formula? Because what do you mean by that? Here's a formula. Okay, so let Pn be the nth perfect number. Okay, then define f of. Here's my formula. Okay, all right. Do you know what I mean? Okay, so when you ask about formulas, you have to be very specific about what you mean by formulas, and therefore I would not ask any questions about formulas, right? Yeah.
Is there a closed form for the
That's a closed form, right? So you have to figure out a sort of a more precise way of saying what you want, right? You can say something like, is it a polynomial expression in n? Okay, does that make sense? Is there a polynomial? Is there but you have to define that very carefully, okay? And we can talk about how to do that, okay? You were talking about gaps. Let's talk about gaps. Tell me what you mean by gaps.
Well, I mean, like how, we're trying to find bounds for gaps between primes. Like, can we bound the gaps?
Okay, how would you say that specifically?
The difference between Pn and Pn minus.
Okay.
How is that related to n?
Okay, you have to ask a yes/no question. So here's a question. Okay, so suppose we know 2. Okay, right? Let Pn be the nth perfect number. Okay, does the limit as n goes to infinity of Pn minus 1? This is called a gap, right? The gap is given by the difference. Here's a gap. Here's a gap. Here's a gap. What do you want to know about the gap? Is it infinity? How's that? Does it make sense? Okay.
Or even with the limit as n goes to infinity, Pn minus Pn over 1 over n.
Yeah, or you can ask this question right here, okay? That's a perfectly good question. Or this question right here, okay? These are all excellent questions that most people, we don't know the answer, okay? Right? This should be true. This should be true. But I think that if you divide it by something like this or this, that gets more difficult. Okay? So do you understand the types of questions I want you to ask? Okay? So what I'm going to do, okay, is I'm going to give you a list of numbers with interesting properties, like 4 of them, okay? And I want you to start asking questions about them, okay? This has nothing to do with Galois theory, okay, at first, okay? But then there's going to be the questions about Galois theory will start. Make sense? Okay, I want you to learn how to write questions because if you want to be a research mathematician, right, these are the questions that you have to ask. Okay? And you have to know what questions to ask before other questions. Like this is a perfectly good question right here. Okay? But it's much harder than asking this question. So it's good to sequence them carefully. Okay, let me see if I okay, let me talk about something called a principal. Okay. Okay. So, just in the last few minutes, we have seen, okay, that this object right here, which is defined to be this, which we know now is this, right? Okay, is an ideal. Okay, so we just proved that, right? This is defined to be the intersection of all ideals that contain B. This is what it turned out to be, so now I can write this, okay? We call, okay, B a principal ideal, okay, right? A principal ideal, okay, is an ideal that is generated by one object, okay? So loosely, okay, a principal ideal, okay, is one that can be generated, okay, by one object. Okay? So here we call this the principal ideal generated by B. Are we okay with that? Right? So what I want to claim is the following. Okay? Okay. Oh, yeah. Every ideal, okay, in Z is principal. Okay? Right? So for example, okay, I have an ideal. Suppose I have an ideal, okay, that has 5 and I don't know, like 20 and 15 in it, okay? Suppose I have an ideal with 20 and 15 in it. What is it secretly? It's just 5Z. It's just, right? If you work this out, okay, you'll see that the ideal that contains both of these numbers and nothing more, right? The smallest thing you can possibly get is this. So any ideal that you can write down is actually like this. Okay? All right. So here's the proof. Okay. So let I, okay, in Z be an ideal. Okay. If I is trivial, what does it mean to be trivial? It's just 0, right? And then I is just generated by 0. Okay, is principal. Otherwise, okay, I has non-trivial elements, non-zero elements. Make sense? Okay. Now, because we're in the real, so I is a whole bunch of numbers, right? 0, 8, 7, 4, negative, blah, blah. Okay, here's I. Let A be, okay, the smallest positive number, okay, number in I. How do I know that there are any positive numbers in I? What if they're all negative? Yeah? It's closed under inverses. Okay, so if you have a negative number, you have a positive number. There's always a positive number there. Okay? Make sense? Okay? So we claim, okay, that A equals I. So the smallest object, okay, generates all of I. Make sense? Okay? Now, one direction is obvious. Which one? The forward direction or the backward direction? This is the forward direction, and this is the backwards direction. Huh? The forward direction is obvious. Why is that? Because I contains A. And A, this guy right here, blob, this A, is all possible products of A. But I is an ideal, so I sucks in all possible products of A. So therefore, okay, as clear as day, okay, this guy isn't. Does everybody understand this? Mean J, is that okay? Right. Let's do the other direction real quick. Okay. Ugh, okay. So let's not do it so quick because time is up. All right. So we'll please finish this. Okay. And the way to do it is to execute the division algorithm. Okay. Let n be an I. Okay. And execute the division algorithm on n and A. Make sense? Okay. And minimality. Remember, whenever you have smallest, that has to come in. Okay.
Why is there a smallest positive number?
Huh? Why is there a smallest?
Greatest common divisor is
What? The well-ordering principle. You could not do this, right, with Q, right, because there is no smallest positive number. Okay, so when you're in Z, you have well-ordering. Thank you. Everybody all right with that?